Thank you. Sorry, proceed.
All right. Thanks, Wilson. Thanks for the invitation. Thank you, everybody, for being here. I am going to be talking about a problem that I'm currently working on. I'm going to introduce the problem. But really what I want to do is show you along the way of trying to solve this problem, we ran into an interesting zeta function, local zeta function, or something that's like a local zeta function, which right now I'm calling a regional zeta function, but that might not be the best name. Yeah, so I want to explain the setup and show you where this integral comes from, and then I can show you a few things that I know about this local or regional zeta function. So just a little bit of a word of warning here. I am originally a number theorist. I still do number theory, but most of my interest in local zeta functions and p-adic analysis has come from random matrix theory, where I've done a lot of work kind of generalizing results that are true on R or C to results on QP or other non-Archimedean completions of number fields. This problem here, though, that I'm about to talk about, it doesn't have an analog for the rational numbers. And so we, honest to God, have to move to a number field, to some sort of extension of Q in order to talk about the problem. So there is a little bit of more notation than if we were just doing classical p-adic analysis, but the ideas are very much the same. So I'm just going to talk through this. Let K be a number field of degree D. I'm going to assume it's Galois over Q. You know, all of these things, that will introduce some simplifications later, but don't worry too much about what it means if you're not currently thinking about number theory or Galois fields. It's just a simplifying assumption. So there is a ring of integers, very much like the integers and the rational numbers. And there are ideals that live in that ring of integers. And then there are principal ideals. Now, the difference between number fields and Q, well, there's lots of differences, but one of them is that in general, in Q, all ideals are principal. So there's no non-principal ideals, but more generally, there are non-principal ideals. From ideals, we can make the group of fractional ideals. There's a couple ways of doing this, but what we're going to do is just formally say that a fractional ideal is an ideal divided by another ideal. We can do this formally, but there is a more precise algebraic definition as well. So these form a group under multiplication. The set of principal ideals is a finite index subgroup in the group of fractional ideals. And the quotient is called the ideal class group. We're not really going to use that very much, but it's an important object in number theory. And yeah, there's still lots of open questions about it. Now, the important thing about fractional ideals, and really the reason that they were originally introduced back in the late 1800s, is that fractional ideals have unique factorization into prime ideals. So if I'm given any fractional ideal, I can find a bunch of prime ideals and unique integers such that the ideal, I'm calling it X, equals P1 to the M1 times ... PL to the ML. This is just unique factorization. Here, because I'm dealing with fractional ideals, you should think of these a little bit like rational numbers. The m's here could be positive or negative. If the m's are just all positive, then you have an integral ideal. But in general here for fractional ideals, the m's could be positive or negative. All right, and that factorization is unique. So scrolling down a little bit. There is something called the norm of an ideal. I give the definition here, but really what you should think about for the purposes of this talk is, since we have a group of fractional ideals under multiplication, then the norm is a homomorphism into the integers. So basically the norm of an ideal is an integer. It's basically telling you the size of that ideal. But it's a multiplicative homomorphism, and that is extremely important. All right. Now I do need to talk a little bit about how these norms work. This is important, though it's a little bit boring. So if basically, if I'm given a prime ideal up in my number field K, if I intersect that prime ideal with Q, right, my number field is an extension of Q, so Q is living in there. If I intersect my prime ideal with Q, then I get an ideal in Q, and it turns out that that thing is still prime. And so therefore, the ideal that I get in Q must be of the form Z mod PZ. So if I have a prime upstairs, there's a prime downstairs associated to it, right? And we say the prime upstairs is over the prime downstairs. Or we might say that the prime upstairs divides the prime downstairs is another language. Now, it's not hard to see, you know, if you follow the technical definitions, that if you have an ideal over a prime, then the norm of that ideal upstairs is going to be P to some power, right? And it turns out that that power is called the inertial degree of the prime ideal. And it's just something that's associated to that prime ideal. All right, what do I want to say next? It is possible, so if you look at all of the prime ideals that lie over the prime P, so the prime P downstairs is a rational number, I can form a principal ideal from that upstairs, right? So I can basically say, oh, I'm going to look at the ideal generated by this rational integer upstairs, right? And then I can factor that ideal upstairs. And it turns out that that ideal upstairs is going to factor into products of the primes that are lying over P, right? So basically, this is just the observation that when you move to a number field, primes in the rational numbers may no longer be prime. They might factor, or their ideals might factor. And this does in general happen. And so in general, what happens, most of the time what happens is if you have a prime downstairs, it's going to factor into a product of primes upstairs, but all the primes upstairs are just going to show up with a power 1. Right, they're basically just going to show up, but they're not going to show up in multiples, right? So in some sense, we can say most of the time, the prime P, the ideal upstairs, most of the time that's square free, right? Occasionally it's not. When it's not, so when a prime downstairs factors into something where you have a higher power of a prime upstairs, that's called ramification. In general, ramification is bad or just different from the non-ramified situation, and it introduces complexities. However, there is a nice thing that there's only finitely many ramified primes for any number field. So while this is a problem, it is a problem that only occurs at a finite number of primes. Right? At any rate, all of this is just kind of background number theory. The important part to say is that if I take the product of the ramification degrees, so the product of how many times a prime appears upstairs, times the inertial degree, right? That's basically the exponent that gives me the norm. If I take the ramification degrees and I multiply them times the inertial degrees, and then I sum that over all primes upstairs, I just get the degree of the number field. Right? And again, this is not too hard to see. This is not magic, but it's a fact that we will use. Now, here's a simplification that we are going to put ourselves in. If we're in a Galois field, and let's just assume that we are, then it turns out that all of the ramification degrees for a prime, for primes above a given P are the same, and all of the inertial degrees for a prime over a given P are the same as well. So in this situation, it's just easier because all the primes upstairs kind of do the same thing. They have the same inertial degree, they have the same ramification degree. Useful simplification that we're gonna use here. Okay, next we need to talk a little bit about Archimedean absolute values. So Archimedean absolute values are just usual absolute values on R or C or something like that. And so we have this field K, this number field. Number fields come with embeddings into the real numbers or the complex numbers, depending on the structure of the number field. But it turns out that for Galois number fields, either all of your embeddings are into R, and you have D of them, or all of your embeddings are into the complex numbers and you have D over 2 complex conjugate pairs of embeddings, right? But at any rate, once you take a field and you embed it into R or C, doesn't matter which, right? R and C come with their own absolute values. And so we can restrict those usual absolute values onto the thing that we have embedded into R or C. And this gives us an absolute value on the number field. Right? These are called Archimedean absolute values because they come from the real and complex absolute values, which are called Archimedean absolute values. All right. There is another kind of norm. We have talked about the ideal norm. So we've talked about norms of ideals, but there's also called a field norm. And this is another homomorphism. Instead of taking in ideals and spitting out an integer, it is going to take in numbers in the field, right, and spit out a rational number. Right. I should say the ideal norm also spits out a rational number. If it's a non-integral ideal, you will get a non-integral norm. And the same thing is true here. The nice thing is there's kind of a convenient way to represent the field norm. And so basically, if I want to know the field norm of an element, what I do is I look at the absolute value in all of its different embeddings, Archimedean embeddings, and I just take the product of those absolute values. Right, so basically the norm is the product of the usual absolute values on the elements in your field. Right? It turns out that if you look at the principal ideal generated by an element, then the ideal norm is equal to the field norm for that in that situation. All right. At any rate, what do I want to say here? There are some special elements in the field with respect to the norm. The norm is a homomorphism, multiplicative homomorphism, and therefore the things that have norm 1 form a subgroup. And in particular, the things that have norm 1 and are integers are called units. So that's the group of units in the number field, but there are other things that have norm 1 that are not units, and that's what we're going to be studying. Right. So I'm going to introduce a map. We're calling it the log map. Sometimes it's called the regulator map. But basically the idea is I have an element in my field. I have a number of different embeddings for my field into R or C, right? And then what I do is I just look at the absolute value of my element in each one of those things. And then I look at the log of the absolute value, right? So basically I'm just taking the log of the absolute value of all of the Archimedean absolute values, and I'm putting them into a vector, and I'm calling this the log map. All right. Now, one thing to notice about the log map is that, well, it gives us a way of embedding our elements multiplicatively into Rn, where n is either d or d over 2, depending on if we have complex embeddings or real embeddings. But it allows us to embed our field into a additive Euclidean space. That's what the log is doing. It's turning multiplication into addition. So it's just basically translating elements of our field into elements in a Euclidean space. And it turns out that if you think about what's happening to elements of norm 1, right? Well, elements of norm 1, that means the product of the absolute values equals 1. That means the sum of the logs of the absolute values equals 0. So everything of norm 1 actually ends up under the log map in a codimension 1 subspace of this Euclidean space, because you have this one constraint, which is norm 1, which translates to sum of logs equals 0. Right? So everything with norm 1 goes into this subspace, including the units. Okay, so the units are in the subspace as well. And Dirichlet, his unit theorem, or at least a version of his unit theorem, says that if you look at the units under the log map, that these things form a full rank lattice in that codimension 1 subspace, right? So if you look in that codimension 1 subspace and you look at the units, you just get a lattice. Think of it as just kind of looking like an integer lattice in that codimension 1 subspace. All right. Other things of norm 1 go into that codimension 1 subspace as well, right? There are things that are not units that do have norm 1, and they will also go into that codimension 1 subspace. The nice thing about that codimension 1 subspace is, well, we have a full rank lattice in it. And so if you mod out a Euclidean space by a lattice, you get a torus, right? And we're going to call that torus T. And the nice thing about that is, of course, tori are compact abelian groups, right? And so they have natural measures on them, natural translation invariant measures that is basically induced by the translation invariant measure on the Euclidean space. But at any rate, these are tori are nice places to do analysis. All right. We will come back to that torus. It is important. But I want to talk about heights. So a height in general is a way of measuring complexity of algebraic objects, right? So there's all sorts of different heights out there, depending on what sort of algebraic object that you're looking at. What I want to do is associate a height, a measure of complexity, to the ideals that live in my number field, right? So, well, one way of doing this, maybe, well, I don't know if it's the most naive way, but it's a fairly naive way of doing this, is to say, well, each fractional ideal I can factor into a ratio of integral ideals, A over B, and I can do this in such a way that those ideals are relatively prime. There's no extra factors. I can cancel those. This is just from unique factorization. And then I'm just going to define the height of my ideal to be the maximum of the norm in the numerator and the norm in the denominator, right? So in general, those are integral ideals, right? The only integral ideal that has norm 1 is the entire ring of integers. So in general, the height of an integral of a fractional ideal is going to be a positive integer. Most of the time, it's going to be greater than 1, unless you happen to pick the fractional ideal. That's all of O. At any rate, we're going to be looking at elements of norm 1. Remember, elements of norm 1s are the things that map into this codimension 1 subspace. And so if I look at an ideal of norm 1, then what you see, well, if it has norm 1, then the norm of A equals the norm of B, right? And so the formula there, we can get rid of the maximum if we wanted to, or alter it in other ways. And then the set that we're going to look at is N prime of T. This is the set of principal ideals of norm 1 whose height is less than or equal to T. And the question we have is, how do these things distribute as T goes to infinity? So one thing to say here is we can embed every element of norm 1 into this codimension 1 subspace, right? That gives us elements of norm 1. But when we move to the torus, we are modding out by units in order to make the torus, right? And if you look at an element of norm 1, right, and then you mod out by units, essentially what you're looking at is you're looking at ideals of norm 1, right? Because two ideals, well, two generators of the same ideal just differ by a unit, right? So if I had picked a different unit in the same coset, I would get the same height. Okay, but at any rate, our fractional ideals of norm 1, principal fractional ideals of norm 1, embed on this torus in some way. And the question which I will not be able to answer, but gets us part of the way to showing you a zeta function that you might like, is how do these points distribute in this torus? And of course, without any other knowledge or reason to suspect something different happens, we expect that these things would be equidistributed in the torus. So what that means is that if you take any open ball on the torus, and you look at the number of things with bounded height that land in that little open ball, right? And you look at the proportion of them, right? You just say, oh, 50% are landing in this ball or whatever it is, right? If you then take the limit as the height goes to infinity, so you're looking at the asymptotic relative frequency of landing in that little ball B, you get equidistribution if that asymptotic relative frequency is equal to the volume of the ball, the normalized Haar probability measure for the ball. And this is basically just saying that equidistribution means that the proportion of points that you're going to sweep up is equal to the volume of the set that you're looking at. Right? This is quite sensible. So then the conjecture is that our ideals of norm 1 are equidistributed in this torus with respect to the height. There's a criteria that we can use. It can be sometimes difficult to use the definition of equidistribution. So if I can't use the definition of equidistribution, there is a theorem of Weil called Weil's criterion, which basically says that we can translate the question of equidistribution into a question of character sums. So it goes something like this. If on this torus is a compact abelian group, it has a lovely set of characters. These are continuous homomorphisms into the circle in the complex plane. It turns out that that's going to be the set of characters is a lattice in this case, because there's this nice correspondence between the structure of the group and the structure of the group of characters. But at any rate, there are characters on this torus, homomorphisms, and we get equidistribution if we can show for non-trivial characters, if I look at the character sum. And so I'm taking all of my elements of norm 1, whose height is less than or equal to t. And then I'm hitting that with a character, and I'm looking at that sum. And then I'm taking the limit as t goes to infinity. Well, there's a denominator there. But basically, I'm looking at the character sum of this thing as ordered by height. Right. And it turns out that if you can show that for non-trivial characters, that character sum equals 0, well, the character sum normalized as you see right there equals 0, then you will get equidistribution. Right. And I didn't put this section, let's talk about the associated global zeta functions. Right. So if I look at this character sum right here, so this is the function t goes to the sum of characters of ideals of norm 1 whose height is less than or equal to t, right? This is the summatory function for a zeta function. So whenever you have a zeta function, you can make a summatory function by basically summing up the coefficients of that zeta function up to some t, and then you say that's a function of t. That's called the summatory function for the zeta function. And it turns out here that this character sum right here is the summatory function for this zeta function. So let's just go over what it's saying. It's a sum over ideals of norm 1. I'm going to hit those ideals with a character upstairs. Remember, these ideals of norm 1 live in this torus. This torus has a character, so that's perfectly well defined. And in the denominator, I'm going to put the height of the ideal to the nth power. Okay. I have this little prime here on z prime. That does not indicate a derivative. Primes are just saying, hey, we're looking at principal ideals here as opposed to all ideals. All right. But at any rate, one has to be a little bit careful here, but one can extend the notion from just summing over principal ideals to summing over all ideals. It's a little bit more complicated because you have to make sense of what does a character mean on an ideal of norm 1. That ideal of norm 1 might not naturally be embedded in the torus. So there's a little bit
Chris,
that needs to.
Sorry,
Yes?
a question about the convergence of zeta and zeta prime. Is direct? Or I don't see the convergence of this series. You have to compare them with what?
Yeah, so they converge. So you can show that they certainly converge when the real part of S is sufficiently large. Depending on how you normalize that, you can do kind of a renormalization here and make it so that they converge in the half plane real part of S greater than 1. I think naturally without that, they converge in a half plane of real part of S greater than the degree of the number field, but that's something that can be shifted away.
My question is the convergence is a direct matter, or really you have to work a little bit to establish a region of convergence for this series?
Yeah, it's not that hard. Basically, because what it comes out in terms of the norms, and so you can kind of just argue that that the region of convergence is related to the regions of convergence of regular zeta functions, classical twisted zeta functions. Yeah, it's not that hard. There is definitely a region of convergence. You have to do a little bit of work, but not a lot of work.
Okay, thank you.
Right. Yep. Okay, so one can also make a global zeta function here. Again, one has to make sense of what the character of an ideal of norm 1 means. I'm not going to worry too much about that, except to say it can be done. All right. Now, here's something that's interesting about the ideal height. The ideal height is not multiplicative, right? Normally, if we look at the zeta function right here, normally what you would hope is that whatever is happening down here in the denominator is multiplicative, because if what's happening down there in the denominator is multiplicative, the numerator obviously is, because it's a character. If the denominator is, then you will have an Euler product over prime ideals, right? So if the height was multiplicative, we would instantly get an Euler product into a product over prime ideals in this number field K upstairs. However, the height is not multiplicative. However, it's kind of partially multiplicative. So let's see how this works. Basically, if you think about the height of a prime ideal here, okay, so MP is going to be an integer. We're going to basically take our ideal, we're going to factor it into primes. Here are the powers of the primes that show up in that factorization. This thing has norm 1, so some of these could be positive, some of these could be negative. As a matter of fact, some have to be positive and some have to be negative, unless they're all 0. And then, but here's the thing, when you look at the norm of these things, so the norm of this has to equal 1. Well, the only things, and the norm is an integer, a regular integer. So the only things that can possibly contribute a p to the norm come from primes that are above that p, right? So put another way, I can take h and I can factor it into, well, they're not quite local heights, right? Because they don't go all the way down to multiplication on the ideals in K, but I can factor it into a product over rational primes, because basically in order to have an integer that equals 1, right, that means that all the powers of p have to cancel out. So if I get a power of p here, I have some other power of p here, and the only way that that can happen is from primes above the same rational prime downstairs. Right, so this HP right here is, well, I'm calling it the local height. Maybe it should be called the regional height, because again, it doesn't quite break up into a product over all primes upstairs. We can just kind of clump them into primes based on rational primes downstairs. Okay, but at any rate, we can take the height, factor it into heights over p, and then the height just over p is basically, well, it's almost the same thing that you get here, right? Remember, the norm of p is p to the fp, right? So that power right there is equal to that power right there. And then, right, so if we call this the local height, because we have norm 1 and the exponent of p and the height is this right here, what we see, let me see here, we'll look at it right here, is that what I can now do is I have an Euler product, but my Euler product is over rational primes, right? And then what am I summing up? I'm basically summing up the contributions from the primes, from the ideals of norm 1 that just lie over that prime. Put another way, an ideal of norm 1 factors into ideals of norm 1, each one of which lying over a single rational prime p downstairs, right? And so the factorization of heights, that multiplicativity or submultiplicativity, not sure what to call it, but that almost multiplicativity of the height gives us an Euler product, right? But it's not an Euler product over the primes upstairs, it's an Euler product of the primes downstairs. Okay, and in general, there's not going to be, because the height is not completely multiplicative, there's not going to be a Euler product into the primes upstairs. All right. So if I look at this term right here, it's a product of other terms, right? These terms right here, I'm going to call that the regional zeta function. Again, maybe not a great name, but what I'm trying to do is distinguish it. It's certainly not global. And it's not local in the sense that it doesn't break up into primes upstairs. It breaks up into primes downstairs, right? So it's somewhere between local. It's closer to local than global, but it's not quite local because you don't have that factorization into primes upstairs. But at any rate, this is a zeta function. So it's a sum over ideals of norm 1 that only factor into primes living over the rational prime p. And then I have the character on those things. And then I have the heights of those things to the s power. Okay. So this looks very similar to our original global zeta function. We're just summing over a much smaller set of ideals here, just the ones that factor into primes over p. All right, so I want to this is the object that I can say some things about, and this is what we're going to be talking about. So the question of equidistribution is one for the future, which I hope that I will be able to answer using these techniques. But for now, the question is, what can we say about these regional zeta functions? And that's what I'm going to be talking about for the rest of this talk. Okay, so we're just going to do a little bit of notation. There's some number of primes upstairs. It turns out that we're in the Galois situation, so that's the degree divided by the product of the ramification degrees and the inertial degrees. Most of the time, the inertial degrees are all equal to 1, so most of the time this is just d over fp. At any rate, I can, given a vector, any old vector here, in J, right, and with J coordinates, then I'm going to define a norm. This is probably terrible notation because this is not the P norm, but it is associated to P. And basically what this norm is morally speaking, except for the FP and EP, it is the one norm of the vector M, right? So really it's the one norm times a number there. EP is usually 1. So it's just a constant of the one norm. Again, my notation is not great, but all right. And then the height of my ideal x. So if my ideal x has m of x, that should be m sub p of x, but if these are the powers of the prime ideals upstairs, then the height of that ideal is just going to be p to this one norm thing of the exponents that show up for that ideal. So basically, I've been able to associate to my height, well, something that comes from a norm, a one norm. All right. Okay, so now I can rewrite, if we go back to my original regional zeta function, all I've done here is I've come up with a different formulation for the height there. And so when I write this now, my regional zeta function, this word twisted just means there's a character there. If it's not twisted, that would be a 1. but at any rate, my regional zeta function right here can be written as this character applied to, well, this thing right here is uniquely defining the ideal, so I can define chi of m to be chi of the ideal generated by that. So that's a sensible thing. That's basically this.
Chris, let me make a comment here because now I can tell you something. Really,
Yep.
you are working with a Poincare series attached to a semi-group of valuations of a Dedekind ring with a finite number of primes. And
Okay.
this Poincare series, without the character, has been studied extensively. I can give you reference because the strategy that you are following here is to use to compute the norms using the evaluations associated with the ideas lying over P. And this series, this Poincare series, have been studied extensively in algebraic geometry.
Yeah, fantastic. I would love to see, yeah, additional references. Absolutely. Yeah, yes, absolutely. I would like to, because the more we can understand these regional zeta functions, the more hope we have of gluing them together to talk about the global zeta function, which is at this point really far away, at least in my understanding. All right, so this thing, as you say, Poincare series, this looks much nicer, right? This is starting to look like something which, again, we're just taking P to a one norm, essentially, right? And then we have some characters out front. This is a relatively nice looking object, but maybe that's just because the notation I chose has simplified it considerably.
Except you forgot the S in the notation.
I did. There should be a minus S. You're right. You're right. It should be P to the minus S norm of M. Thank you. There's probably more typos been. All right. So now I want to talk about kind of a generalized situation called Hart McDonald reciprocity. And so here we're going to assume that P is unramified, so we can ignore the EP. Again, there's only finitely many ramified primes. And quite frankly, if we can ever figure out what's going on, if we want to understand the global zeta function, for my purposes, understanding equidistribution, you can throw away a finite number of primes. They're not going to change the equidistribution in the limit. And so we can probably stick to the non-ramified case. At any rate, it doesn't matter. I'm just doing it so I can simplify things a little bit. I'm going to say FP right here is the vector of inertial degrees. When K is Galois, right, that's just a vector of ones. Or well, a constant. Well, okay, at any rate. It basically, what I want here is to look at FP perp. So think of this as being a vector of ones, right? And then I'm basically just looking at everything which is orthogonal to that in RJ. Okay, and so basically what this perp is, right? F perp is essentially the place where the ideals of norm one go. Right, so this condition right here, x dot fp equals 0, is exactly the condition that we are looking at ideals of norm 1. And so therefore the m's, the exponents for those ideals, are a lattice, a free z module, and fp, right? And this norm is the one norm, right? Or constant times the one norm. All right, so what I want to do is to define a closed unit ball in RJ minus 1. So I'm identifying RJ minus 1 with FP perp, right? FP perp, that's a one-dimensional thing. And so that's basically RJ minus 1, or at least I can identify it with that. And so I have a closed ball in RJ minus 1 by intersecting the ball from R1 norm in RJ with this plane, right? So basically I have the one norm ball in RJ. I have this codimension 1 subspace. I am slicing that codimension 1 subspace, or slicing that ball with a codimension 1 subspace, and I get a new ball in my codimension 1 subspace. Okay, and I can define the open unit ball. I did this for the closed unit ball, but I can define the open unit ball in the same way. And then I'm going to use these counting functions. And what these counting functions is, L of t is the number of lattice points in the dilation, the t dilation of that ball. Right? So I have this ball in Rj minus 1. I multiply it by t, it dilates. I have a lattice and Rj minus 1, and I can just count the number of integer points that land in that dilated ball. I can do the same thing with the open ball as well. Right? Not a whole lot changes. What changes is on the boundary, but at any rate, I can do it for the open ball and the closed ball. And then I can make an Ehrhart series. So the Ehrhart series is, well, we take this counting function, right? Now this counting function is really only for us interesting when t passes through an integer. Yeah, that's because all of our norms are integers for our lattice points. So really the only interesting things that can only change when t goes through an integer. And so we can make a generating function for the LTs, for these counting things. So the Ehrhart function, this is the Ehrhart series for the closed ball, is going to be basically, I count the number of lattice points and the dilation corresponding to t, and then I put a z to the t there. This one right here is just because you pick up the origin as well. I can do the same thing for the open ball. I don't pick up the origin on the open ball, but everything else is pretty much the same, just counting the number of things in that dilation and then using that as a coefficient in this generating function. Nice thing about that, right, is if I look at the difference of these two things, well, the difference of those two things are counting things literally on kind of the boundary, right? I'm only picking up points as I sweep through them on the boundary. So if I look at this minus this, I'm really just picking up all of the points, right? Here is z, that's z. I'm picking up basically a z to that power every time that's on the boundary of the object. Right? Does that make sense? Basically, right, this is counting everything on the boundary and inside. This is counting everything inside. So this is just counting everything on the boundary. But that gives us exactly this sum right here, right? Which is useful, right? Because that's very similar to this sum right here. And when the character is trivial, it is equal, right? So why is this useful? Well, this is useful because in this situation, our balls, these BP and BP0, these are integral polytopes. And for integral polytopes, the Ehrhart series for integral polytopes satisfies a functional equation. Right? So this is Hart McDonald reciprocity. And it basically says in this situation that E of z and E0 of z are related by this rather simple functional equation. Right. Of course, this is useful because if we look at the non-twisted regional zeta function, again, the one where the character is always equal to 1, then ZP of trivial character S is the difference between those two things, right? And so that means that the regional zeta function, non-twisted regional zeta function, is a rational function in p to the minus s, right, satisfying a particular functional equation between s and minus s. Right. Now, there is a more general form of Hart McDonald reciprocity. I'm not going to go into it. My time is almost up, but I want to say that this sort of thing, it can be done not just for the untwisted ones. You just have to use a more general sort of reciprocity called Stanley reciprocity. And there, what you see is if you want to look at the twisted regional zeta functions, this is still a rational function in p to the minus s. You get a functional equation, right? This thing right here gives you a functional equation, but so you get something similar for a functional equation. And the only thing that really that changes, and not surprisingly, if you've done any of these things, is the character chi on one side goes to the complex conjugate of the character on the other side. Not surprising. Anybody who's read Tate's thesis has seen a trick like that happen before. All right, so we have these functional equations for the local or the regional zeta functions. Finally, in the last couple of minutes, this is going to be a little bit of a mess. I just want to write down these zeta functions as a integral, a non-Archimedean integral, and show that this, well, and just talk a little bit about it. So finally, what we do is we take our number field K, we can complete it with respect to the absolute value made by the ideal P, right? And that thing is a locally compact abelian group. It has a nice Haar measure. As a matter of fact, it has a multiplicative Haar measure on the multiplicative group there, right? This is basically just notation for people that know what's going on. That Haar measure needs to be normalized. One sensible normalization is to look at the group of units and make, that's a compact set, and make the measure of that compact set equal to 1. I can then make a product measure, right, on all of these things right here, basically just multiply all those measures together. And one thing to say is that in KP, there is a unique maximal ideal, which is the closure of P under the absolute value. So we can just denote it by P again. And the if we denote the local integers in KP by P0, then the group of units is all of the things that are an integer but are not in P. So P0 minus P. This is like an annulus, or at least I think of it like an annulus. And we can define the nth annulus to be basically, well, take the n minus first ideal and subtract out the nth ideal. Because of the way our measures work, all the annuli have the same measure, right? That's just translation invariant. Oops. Well, I was working on this morning, but at any rate, so what we're going to do is we're going to look at a product of these annuli, right, over different integers, one integer for each place P, but we want to have n dot fp equal to 0, right? And then it's not hard to see, none of this is really hard. This is just definitions. I just want to show you this formula, which says that the regional zeta function can be written as an integral over dp with respect to this measure right here of a relatively nice integrand, especially in the case right here where, you know, chi p is equal to 1, right? This is a particularly nice integrand. However, this is the last thing I'll say because I'm at the end here. This particular regional zeta function cannot factor farther into local zeta functions, right? Now, one thing you can do is you can expand ZP, and then when you sum over ZP, each one of the terms will expand into a product of local zeta functions, but the regional zeta function itself does not factor into a local zeta function. So there's really non-trivial dependence between what's happening in one completion of K and what's happening in another completion of K. After all, I can make an ideal of norm 1 by taking the prime ideal from this and dividing by the prime ideal from this, right? So there are actual relations between these things upstairs. So I can't just factor this into a bunch of Agusa zeta functions and say, oh, well, let's just use the Agusa fact about rational functions in P to the minus S. I have to use some additional tools. So this does not follow, the results that I showed today do not follow immediately from Agusa's theorem, though they can be gotten there by some convoluted path, breaking this integral up into several integrals. At any rate, that's all I wanted to say today. So yeah, happy to chat more.
Thank you very much, Chris. It was a very nice talk. Do you have, let me stop recording. Stop recording.